Okay, we're going. Okay, so here's what we're going to talk about today, section 2.3. We're not going to finish 2.3 today. It's just not going to happen. Too much stuff. But we're going to start into talking about some actual multivariable calculus for the first time today here in the middle of the third week of classes. So we're going to talk about derivatives. First thing to know, there's lots of different kinds of derivatives in multivariable calculus. In single variable calculus, not so much, right? In single variable calculus, there's the derivative. End of story. And then various different things you can do with it, I suppose. We're going to see bunches of multivariable derivatives. Now, a little bit of foreshadowing. It is going to turn out that they're all kind of related. They're all kind of different shadows of the same biggest possible derivative, and so in some sense there is only one, but in practice there's a bunch of them, and it's going to take us a while to connect them to each other. So all these different kinds of derivatives, what they have in common, the reason that all these different things, we can use the same word to describe this, because they have this common feature. They all relate input changes to output changes. And I think if you think through the single variable derivative, you probably persuade yourself pretty quickly that, every point of view you have on single variable derivatives, in some sense, is a relationship between input changes and output changes. Okay. All right. So here's the first one we're going to talk about. It's called a partial derivative. Just a little bit of behind the scenes. It's honestly not my first choice of how to start talking about derivatives. I am going to, however, do it in this class partly because this is the choice the book makes, and I don't want to get too far off from the book's presentation. But there are good reasons. It's not a bad idea, but partial derivatives are really easy to compute. We're going to see that momentarily. They're super easy to compute. And having a nice sort of easy first step, it makes sense. I get that. They're also highly familiar. This is going to look a lot like single variable derivatives, and that's a nice thing. It's a nice sort of gentle first step into multivariable derivatives. Okay. All right. So that said, though, I remind you, there's a downside to starting with partial derivatives. There's a tendency for students, whatever they see first, to think, okay, well, fundamentally, this is what the thing is, because you've seen it first. Right? And I just want to warn you that it's really not in this case. Partial derivatives have nice things about them. We're going to be using them a lot. The rest of this course is going to be just chock full of partial derivatives, and yet there is a more fundamental point of view on what a multivariable derivative, how you should think about multivariable derivatives that is not partial derivatives. So I just want to plant that thought. Leave a little space in your filing system of your brain for what for that fundamental point of view is on derivatives, because this should not be it. Okay, so here's how you compute them. We're going to actually do several on the next page. But the general process is we've got several variables, and we're going to hold most of them constant. We've got 3 variables, 5 variables, whatever. Just fix almost all of them. Hold them constant. Don't allow them to change. Pretend like they're a constant, except for one of them. That one variable, whichever one, you can pick any variable you want, but whichever one, that's the one that's going to remain a variable. And if you think about it, what you now have is kind of a single variable function, because your function may actually depend on several variables, but most of them are constants. Is a constant really not really a variable anymore? So you kind of have a single variable function. Okay, all right. And once you have a single variable function, single variable function, take the usual derivative. Just exactly plain old, regular old Math 111L derivative. Okay. Now before I get to computing, let me note some notations. This is what I'm going to call the most common notation for partial derivative. It looks kind of like Leibniz notation for single variable derivatives, you may notice. And the big difference is that this is not a D. It looks vaguely like a D, and I suppose that's deliberate. But it's not. It's not a D. It's just called the partial symbol. It doesn't have another name that I'm aware of. Very important though, it's not a D, and you can't substitute a D. A D would mean something different that this is not. So you can't put a D there. Be very clear about that. Also, heads up, a lot of people think this is a lowercase Greek letter delta. It's not. The lowercase Greek letter delta, you're going to notice kind of at the top, it kind of falls over to the right there, and the partial symbol doesn't. So again, very important that you not use either of these. It's a new symbol. You might have to, kill half a sheet of paper by kind of practicing, deciding if you're going to sort of start on the inside and spiral out, or start on the inside and spiral in. I don't know. There's different people make different choices. There's no right answer there. But anyway. Okay. So now another thing I'll point out: this notation here. It looks like a fraction. It looks like we're taking this thing, as if it's a well-defined thing on its own, and dividing by this thing. And importantly, that's just not the case. This is really, honestly, it's just notation. Don't think of this as a ratio of two things. It's just it's notation to represent something that's kind of like a derivative, and so we use a notation that's kind of like a derivative. Okay, all right. There's also this kind of subscript notation where whatever the variable is that you're taking the partial with respect to, just make it a subscript. This is what you might call Newton-like, right? This is kind of the partial derivative version of like f prime, right? And we'll use that sometimes as well. Okay, pros and cons. Okay, let's do one. Going to compute a partial derivative here. Notice we're computing a partial derivative here with respect to y. That means y is our variable. That means all of the other variables are being held constant, right? So x and z are to be treated as constants here because, well, they're not y. Y is the only remaining variable. So e to the x, constant. Cotangent of x squared e to the z is a great big complicated looking constant. Still constant is the point. So here's the thing. What we've really got here is we've got a just y squared times a constant. And if you're taking the derivative of y squared times a constant, it's really easy to do, right? The derivative there is just 2y. Everybody on board? So keep in mind, two-step process. Step one, hold everything constant except for the variable you're taking the partial with respect to. Step two, just take the regular old, plain old derivative with respect to that variable. Everything else being treated as a constant. Questions? Is everybody happy? Okay. And then, of course, at the end, obviously, aesthetically, it kind of looks better if you put the 2 over there on the outside. So clean it up after you're done. But the actual computing of the partial derivative is just this. Okay. Let's see another example or two here. Taking a partial now with respect to x. That means that I've got a function here, x squared plus 1. That's still a function, but this exponent, y squared, keep in mind, x is the variable. That means y is a constant. That means y squared is a constant. And so this is not a function to the power of a function, particularly, because we're taking a partial derivative. That exponent is a constant. It's a weird-looking constant, but it's a constant. And function to the power of a constant, you use the chain rule. What do they call it? The generalized power rule, I think they like to call it. Like so. What do you think? Is everybody okay with that? Okay. All right. Oh, here's another one. So here we're taking the partial with respect to z. Well, if we're taking the partial with respect to z, that means that x and y are constants. That means that x squared plus y squared is a constant. This, again, it looks like function to the power of a function. This is really constant to the power of z. This is a basic exponential. And so, again, there's an old fact from single variable calculus about how to take the derivative of a constant to the power of z. Hope that looks familiar to everybody. How do y'all feel about that one? Is that okay? Okay, so I think I've shown here that these really are easy to compute. Right? So, in fact, they're so easy to compute, I claim they're kind of, in a way, easier than single variable derivatives to compute. Because when you're computing a partial derivative, you get to just take large parts of your function and say, hey, you know what, that's a constant. Right? Wouldn't that be nice if you could do that in a Calc 1 class? Just be like, I'm going to take this whole thing over here and just treat it as a constant. So, easiest derivatives to compute that I am aware of. Okay. All right. Okay, next question though. Is this useful for anything? Does this relate to the real world in any way, or did I just make up a silly construction that doesn't relate to anything, doesn't have any practical application, right? What's this good for? What does it mean? What does it look like? What does it relate to? Natural next question. So we're going to talk about the geometric interpretations of partial derivative. There's several different points of view we're going to have to take. And because keep in mind, if you want to talk about a geometric interpretation, it depends on what kind of a picture are you looking at, right? We made a big deal over the last couple of class meetings that graphs are entirely different constructions from level sets, for example. And so how you interpret calculus on a graph is very different from how you interpret calculus on a level set. It's a very different calculus of level sets than calculus of graphs. So we are going to have several answers to this question. We're going to start, just to get the ball rolling, we're going to start by looking in the graph world, right? So notice we're looking here at a graph of some function of two variables. And on that graph, given that we're in this graph picture, what do partial derivatives look like? How do I interpret partial derivatives? We are now doing calculus of graphs. Okay. Alrighty. Okay, so first thing we're going to do, arbitrarily, I'm going to choose to think about the y partial. No particular reason. Just to get the ball rolling. So what does the y partial look like? All right, well, we've got a set of rules for how to define a y partial. When you're taking a y partial, it's kind of a two-step process. And in that two-step process, each of the steps has an existing geometric interpretation, I claim. And so really all we have to do is just kind of keep track of what's happening as we go along. So, for example, keeping in mind, we're taking the partial derivative with respect to y. That means that if we're interested in a point here, a comma b, in the domain, it's at that point that I want to compute the partial derivative. Well, x is fixed. That means x has to, if it's a now, it's got to stay a for the purpose of computing the partial derivative. That means that I am confined to this vertical plane. This is a kind of a vertical cross section, you might say, of space. That's where x is equal to a. Yeah. Which you'll notice, now this is just kind of a geometric observation, but it's a plane that's defined by a fixed value of a, and so it kind of sort of points in the y direction, if you will. Right? In other words, as you move along in this plane, you're moving along in the y direction. So we were looking at the graph. We were looking at this whole surface. We are now interested only in what's going on in this gray cross section, and so we are now actually only interested in, for example, let's say that curve. Everybody with me? So the whole business, the algebraic idea of fix x and reinterpret your function as a function of just the one variable y. This is what that looks like. Fix x, viewing now as a function of just y. And let me also point out the value of the function. The value of the function is still height. And so I've got height being the value of the function and my variable y going in this perpendicular direction. That means that this purple curve is actually the graph of my single variable, my new single variable function of just y. So I'm looking at a graph of a single variable function. All right, next step, by the way. Next step is to go ahead and take the regular old single variable derivative. And here's the thing. Again, we've already established, we just got through establishing that we're looking at the graph of our new single variable function. This curve, that cross section, is the graph of my single variable function. I want to take the derivative of that single variable function. What does it look like when you take the derivative of a single variable function when you're looking at the graph? And the answer is the slope of the tangent line. Right? So this process of taking a y partial, fix x, interpret it as a single variable function of just y, take the derivative with respect to y, that results in the slope of this tangent line. And so there's our punchline. This is what partial derivative with respect to y means. It's the slope of the tangent line to the graph of f. I didn't circle that very well, did I? Let's try that again. There we go. Slope of the tangent line to the graph of f. Yes?
I was just kind of wondering how, graph calculus can be useful, because you're going to need, an equation of some type anyway.
Yeah.
To, take the derivative and stuff.
Yeah.
How is just, looking at a graph useful? Wouldn't it be, make more sense to, look at, specific functions?
At the algebra?
Yeah.
Yeah. I mean, a lot of math is really kind of moving back and forth between algebra and geometry in some sense. I mean, the physical world we live in is geometric. Whether it's convenient or not, we live in a geometric space, right? But algebra, as you correctly point out, is really easy to do business in. I've got theorems and properties and tricks and that kind of thing that I can do with algebra. So very often, we have a geometric question. We translate that into algebra. We do the work with the algebra. We take our result. We want to then reinterpret that back geometrically. Right? Why deal with graphs? Well, because that may be the connection that I need between the algebra and the geometry, right? Like maybe I'm looking at I've got an umbrella sitting over a picnic area. Maybe that umbrella is like a paraboloid. It's geometric, right? It's a geometric thing. Now, how would I study that? I might say, well, that paraboloid is the graph of a particular function. And knowing that I've chosen to interpret this as a graph, and knowing as I do calculus of graphs, then I can apply calculus of graphs to that function whose graph is my umbrella. Does that make sense?
Yeah.
Yeah. No, it's a great question though, because a lot of what people think about as being math is algebra, and I don't know, I like to think that math includes really both, and again, not all, but a lot of math. Certainly a lot of math in this class is going to be kind of moving back and forth between very often geometric questions, algebraic tools, and then reinterpreting as geometric answers. Yeah. Okay, super question. Thank you. Anybody else? One little detail that I left off is that because we're taking a partial with respect to y, when we say slope of the tangent line to the graph, I have to say specifically in the y direction. After all, if you look at your graph, here's our graph, right? There's lots of tangent lines at that point. Yeah, there's that one, but there's also one there and one there. There's really an entire plane. if you will, of tangent lines at that point, because it's a whole two-dimensional surface. So if I just say, oh, partial derivative, it's the slope of the tangent line, which one? There's too many. So we've got to specify exactly which one. And because it's the partial with respect to y, that's what means that we're looking at the cross-section in that y direction, and thus the tangent line, the tangent line that points in the y direction, or you might say the tangent line whose projection down into the xy plane points in the y direction. Yeah?
Can you do like a partial derivative in a certain direction?
That's a great question. So you're wondering, does it have to be an axis direction, right? So we just talked about y partials, and then you could imagine x partials. You're wondering, can I do a partial derivative that way? Kinda. It's just that we don't call them partial derivatives. There's another name that we have for it, and it's a very natural thing to ask about, so super question. We just don't call it a partial derivative. There's a different name, and to avoid getting ahead of ourselves, maybe I won't say it just yet. But yes, we will absolutely be doing this. Yep.
Well, that worked because you had one output, but you could have a graph of, like, say, one input and two outputs.
That's right. And that is a harder thing to talk about, and so I'm going to mostly not deal with that. Graphs. Well, again, they're dimensionally awkward, right, because there's so many variables involved. And yes, you can have a graph of a function from R1 to R2. It's just not going to come up much in this class. Yep. Okay. So here's what I'm going to do. I'm going to leave as an exercise for y'all to take what we did to the y partial, how we analyzed the y partial, and ask you to reason by analogy, go through this whole process, adapt as necessary to answer for yourselves what would it look like to take the partial with respect to x. Again, it's going to be a lot of the same reasoning. You're holding something constant. You're moving in the direction of something else. There's a cross-section plane. It's going to be a different plane now. It's going to be a perpendicular plane. But still you're taking a cross-section, and you're going to get a curve, which is a graph, which you're going to take the slope of, and think it through. I claim this is the answer you'll get. Again, it's the slope of a tangent line to the graph. It's just that it's the one in the, we're taking the x partial, and so it's the one in the x direction. Okay. All right, so again, nice exercise. I hope you'll take a few minutes. Give yourself the challenge of actually drawing the pictures and thinking through all the details to persuade yourself that that's right. Okay. All right, now again, all that was graphs. There's more calculus of graphs that we're going to talk about as we go along, but for the moment, we're going to set that aside. We're going to now look in a different picture. Remember, not all pictures are graphs. We have these other kinds of pictures. This is one of my favorites, actually, but I call it the literal picture. You'll recall we talked about this before. And notice, if you've got a function whose domain is R3, okay, I can draw R3. There it is. And if the target is R1, well, okay, I can draw R1. There it is. And if the function, if what it does is it takes points in the domain and it returns points that are in the target, okay, well, that's generally speaking what we're going to visualize happening in this picture is stuff in here is going to have images that are in here. So, again, literal picture, not a graph. So, our partial derivative, what does that mean? What does that look like in this context? That's not a slope. It's just not. Okay. So, okay. What is it exactly? Keep in mind, y is our variable in this example, analogously for other kinds of partials. But if y is our variable, that means that x and z are fixed. That means that x, for the entire purposes of this whole calculation, x must always be A, z must always be C, which means that we're going to be confined to that line corresponding to x equals A and z equals C. And we're then going to note that we have kind of a what you might call a single variable function left over. And by the way, one-dimensional domain, one-dimensional target. This really is very familiar as a single variable function at this point. And so how do we interpret derivatives? What is a derivative in single variable calculus? Well, again, different points of view, but the point of view I'm going to take here is that the derivative is the thing that you multiply by input changes to get output changes. Right, one of several interpretations you could take. And why am I taking this one? Well, because I see the input change and I see the output change. I don't have a graph to look at. In this context, it wouldn't make sense to think about derivatives as being slopes of tangent line. I don't have a graph, right? But this is the one that makes sense here, where I can see an input change, I can see a corresponding output change, and the derivative relates them. The derivative is the factor you multiply by the one to get the other. So that's my interpretation of partial derivative on this picture. And it's not, it's not geometric. It's not sort of, satisfying in that sense. Sorry about that. But that's what we get in this picture. Okay. Alrighty. Moving along. What if we're looking at level sets? Well, again, it would be kind of nice to have it be something I could point to. Like, wouldn't it be nice if it was like the slope of the level set? It's not. Right? I emphasize it's not. But we're just not going to get that kind of satisfying kind of answer. So we've got to, again, think through what happens when you do any one of these calculations. Like if I take an x partial, what does that look like on this picture? How would I interpret the input change and the output change? And correspondingly get a sense for what that partial derivative is. Well, here we go. X is our variable, so we're moving in the x direction. That means that y is a constant. That means that we're moving on that line where y is not allowed to change. And as we move in that x direction, how much is the function change? Where on this picture do I see how much the function is changing? And where on this picture do I see how much the input is changing? And here's the thing. I can see how much the function is changing by, for example, between there and there. How many contour lines did I cross? If each one of these contour lines, level sets, right? If each one of these, I like to think, when I'm looking at level curves, I like to think about, height being the, what the function represents, because I'm accustomed to looking at topographical maps, right? So each one of these contour lines you can think of as being maybe, let's say 100 feet. Right? So as I move from there to there, notice that my input change is small. I didn't move very far in the x direction. Small input change, and I gained 200 feet of altitude. I'm going to call that a large output change. And that's a large fraction. Right? A lot of output change for a small input change. Okay, by comparison, if I were moving in the y direction, x is constant. I'm moving kind of like that. Right? If I'm moving that way, well, I can still talk about how long it takes me to move between two contour lines. Still 200 feet elevation gain. But instead of gaining that 200 feet over this very short distance, I'm gaining it over this much larger distance. And so you might say larger denominator in some sense. Right? And so you would expect that this y partial would be relatively small. Yeah.
I'm kind of confused what those lines are. Are they like
they're level sets. Each one of these lines is a level curve.
Are they changing in the x direction? Are they in the same x?
Yeah, I was trying to draw curves that are ever so slightly curved, but they're tilted. You might say they kind of lean to the left from the vertical. And I wanted to tilt them that way because I wanted to be able to talk about both X and Y. I wanted to have, again, one of them be very different from the other one. So yeah, they're kind of angled, almost vertically, but slightly counterclockwise from vertical. Yeah. Is that good?
Yeah. So they're kind of like the X at the bottom. There should be all the same, or
wait, what now?
The point is being on the x-axis. At the bottom, should those all be like the same value?
You talking about these points down here? Well, those are different values of X because they're on different curves. And keep in mind, you're talking about the input X coordinates. You're talking about the output altitudes.
Yeah,
The altitudes are 100 feet different for each one. I'm just saying. So 500, 600, 700, 800, 900, something like that. So yeah, altitude change of 200 feet this way, and this is that same altitude change going the other way. Yeah, right. So one way you can think about this, and I find this satisfying. I've seen topographical maps enough that I don't know, it seems natural to me. Think about if this were in fact a topographical map, which of these two roads would you want to drive in your car? And the thing is, that would be a bonkers steep road. You're gaining hundreds of feet of altitude over presumably fairly short horizontal distances. That's going to be super steep. Your car might not be able to do it unless you've got a four-wheel drive with a low gear, maybe a winch, something like that, right? Something ridiculous. But if you're doing this, if your road goes mostly along the contour lines, to the extent that you're going actually along the contour lines, your altitude's not changing at all. It's level. So if you're only going slightly inward of the contour lines, then you have a fairly reasonable slope. So I have a picture here. This is an actual mountain road. This is Mount Evans in Colorado that I drove up just a couple of years ago. And by the way, if you want an exhilarating ride in a car, this is a good one for a combination of reasons. For one thing, as you're driving along these roads, especially as you get up here, it's very, looking off to the side, it's very steep down there. And it's scary because it's literally thousands of feet. Like if you went off the side of the road, your car would stop rolling 1,500 feet down or something ridiculous, right? So it's very scary. Also, you're at a very high altitude, and if you had just flown in from Durham, as I did, and hadn't accommodated yet, at 14,000 feet, you will find that your ability to perceive distances and your reaction time very noticeably reduced. I'm almost a little surprised that it's legal to drive a car at that altitude because it's, anyway, you will not feel in control. And anyway, it makes for a lot of excitement, fear of death. I don't know if you're into that sort of thing. But notice what you're going to notice about the road here is notice how they kind of follow the contour lines, right? So you take over here, for example, there's the road, and the contour lines are, kind of mostly kind of that same, going generally that same direction. So this is a fairly reasonable drive along in here. I mean, you're going uphill, for sure, but you're not going super uphill. And then likewise, everywhere else along in here, you'll notice, for example, this segment of road here, right? And the contour lines are, again, kind of roughly parallel-ish. Not exactly, right? They're kind of curving around and stuff, but you're not just cutting straight up the mountain. That would be crazy, right? If they had made the road like that, no one would be able to drive their car up it. Okay. All right. So again, if you have some sense for contour lines, then you'll have a better sense then for why I say this is a fairly gentle slope. This is a small partial derivative, whereas this, oh my gosh, you're cutting straight through the contour lines. That is steep on the graph. That is a very large partial derivative. What do you think? Everybody good? Okay. All right. Okay, so we're going to talk about we're going to work our way up to some other kinds of derivatives. We're going to get to them by considering this new question of how do we find a linear approximation for a function. And along the way, anyway, after we get to the end of that, we'll be able to look back and see that some of the things that we did actually are, in their own sense, their own kinds of derivatives. But anyway, let's just answer the question first. We'll go back and interpret after. So I hope you all remember single variable calculus. Well, if you have a single variable function, then this right here is the linear approximation. Does that look familiar to everybody? Yeah. Okay, so there's different ways to define the linear approximation. I have a favorite that I think generalizes very nicely in what we're doing here, so I'm going to go with this. I'm going to say this is the linear approximation because this function has the same value as f, and it has the same derivative, the same first derivative as f at the point in question, at this point A where we're computing the linear approximation. So that's what makes this, I'm calling, a linear approximation. It's got the same value as the function we're mimicking. It's got the same derivative, first derivative, as the function we're mimicking. And this is the formula that does it. Now, by the way, I know you've seen this and I know you believe it. But have you ever proved? It's just a calculation. It's not that big a deal. Have you ever directly confirmed that this function has these two properties? If you haven't done that before, I think it's a healthy exercise. Everybody should do that at least once in their lives. It's not hard if you get stuck on it. If you're not sure how that works, come to office hours. We'll be happy to show you. No problem. But everyone should know how to confirm these two statements. Okay, so this is what I'm going to use as my starting point to generalize. When I say I'm going to be looking to do linear approximations of multivariable functions, I'm going to be looking for functions that have the same value and same first derivatives as whatever it is we're trying to approximate. In other words, I'm going to be looking for a multivariable version of these two equations right here. So, all right, let's do it. Whoops. Here you go. Notice this says I want my function L to have the same value as f at whatever the point A is. And notice down here, these are saying I want L to have the same partial derivatives as f at the point A. Now there's several. Right? Functions have several partial derivatives because there's several variables with respect to which you could take partial derivatives, right? So I want, since the whole idea is I want L to be mimicking f, I want it to be copycatting f as much as it can. I feel like it should be copycatting f in all the directions, and namely that all the partials should be the same as f's. Okay, so does everybody see how this is just a multivariable ripoff of this version here for single variable? Yeah?
Why is there the evaluated outline for the function?
Oh, yeah, it's just, it's an alternative note. It's a great question. It's an alternative notation. It just looks weirder. So let me talk about what's going on here, right? I alternatively could have written that as partial of f with respect to x1 at A, and then x1 minus a1. The problem is now I got parentheses next to other parentheses. I don't know. I just think it looks weird. It just kind of, it makes it feel maybe, am I multiplying these two things? You know, it just, I mean, anyway, there's nothing really wrong with this if you want to write it that way, but you kind of avoid the problem when you write it like this instead. Then it's at least unambiguous. But yeah, that's all it is. It's just an alternative notation for evaluate the thing on the left at this point. Great question. Anybody else? All right. Yeah. So, yeah, this is what it means to be a linear approximation to a multivariable function. Notice, multivariable function. Okay. And what's the function that does it? Well, here it is. And you can confirm for yourself that this works. I meant to change the color, sorry. This is the function that has these properties. This is the function that shares value and partial derivatives with f at that point A. And this is another one that I think everyone should confirm for yourself. It's going to be highly analogous to what you did here to confirm that that function has these two properties. That, again, a lot of you probably did in a single variable calculus class. This is going to look a lot like that same bit of algebra. A little bit different because they're partial derivatives. Good news, when you're dealing with a partial derivative, again, you get to view all the other variables as constants. Right? It's awesome. You just get to say, all this stuff here, this is all constants, I'm going to ignore it. It's really nice. But that being the main difference, the rest of the calculation is pretty analogous, and again, I think this is a healthy exercise. So take a little time, make sure that you can confirm that this has these two properties. And again, if you get stuck, come to office hours. I'm happy to help out. And, the help room, you can go to Porter's office hours, what have you. Okay. All right. Okay, now I do have a complaint about this formula, and that is it's kind of big and long, and it's got this ... thing in it that's, it's just, I don't know, it's a little unsatisfying to have that there. So I'm going to rewrite this equation a little bit. I'm going to rewrite it like this. And the only thing I have to do to rewrite it as such is just kind of notice that what we've got here is really just a dot product. It's a dot product of, well, if you look at these coordinates here, there are these things here. Those, you'll notice, are just the coordinates of the x minus a vector. So in some sense, the second vector in what I'm claiming is a dot product up here is the vector x minus a. Does everybody see that part? Okay. What's this first vector? Well, this first vector I don't really recognize based on what we've developed so far in the class, but the vector whose coordinates are the various different partials. It's heretofore not a thing, but I'm just going to therefore make it a thing. I'm going to say, hey, you know what? This thing here, I'm going to define that to be this thing called the gradient. I'm going to use this weird notation here with a sort of an upside down triangle. This is called the gradient of f. And for the moment, it is just this notational convenience. That's it. I don't want you to think, that this is an observation. Oh, hey, this is that thing that we've seen before called... No, this is not something we've seen before at all. This is just I'm going to choose to call this a thing so that I can have a more convenient way to write this down. That's all it is. Is everybody good on that part? Does everybody see how that big expression then gets more compact when I sort of, in some sense, recognize and compact the dot product? Okay. Now, a little foreshadowing. This thing here, the gradient, is eventually, we're going to see, is going to have some neat geometric properties on its own. This is a kind of a derivative of sorts on its own. It's going to take us a little time to develop that, so not just yet. But for the moment, it's just a notational shorthand, and you can be on the lookout for cool interpretations of it. Okay, let's do one. This is very plug and chug. Here's a function, multivariable, two variables. Let's do a linear approximation, specifically at this point. And this is just, like I say, very plug and chug. First thing I need to do is notice what happens to the function. Specifically, what is the value of the function when I plug in this point, A? And, well, it is 5. Whoops. Oh, shoot, colors. It is 5. F of A is 5. Okay, what's the gradient? The gradient, made up of all the partials. Just compute the partials. Don't forget to plug in our point here. We're going to be plugging in 1, 2 in there. So I'm going to plug in 1, 2 there and there. And our gradient becomes this vector, 2, 4. I'm just plugging in, right? And then lastly, we've got this x minus a business. Conveniently, x minus a, well, x is the vector with coordinates x and y. And a is given, 1, 2. So that is 1, 2. And that's what happens when you subtract those. So, plug and chug. That's all there is to it here. And this linear approximation is this. And if you want to, you can multiply out this dot product collect term, and you get this thing down here. In some circumstances, that might be useful. I mean, if you're actually going to be using a linear approximation to punch up a bunch of things, and you need to be able to plug in numbers, and you're going to want to do it a whole bunch of times, you want it as fast as possible, then yeah, sure, you might want to write this simplified form. But honestly, for what we're doing, I mean, I trust your ability to do that trivial algebra there. I kind of find it more satisfying to see the value of the function, to see the gradient, and to see the displacement x minus a. I think this is just fine as it is here. I wouldn't really advise rewriting it from that. Okay. All right. Now you'll notice. Let's see, where am I? Here I am. Multivariable linear approximation that we just did still was real valued. This was only a real valued multivariable function. What happens now if you have a vector valued multivariable function? How would we do a linear approximation of that? Well, again, I'm going to observe that I want to match in value and derivatives. The derivatives should be all the partial derivatives. It should be all the partials, in fact, for all values of the input variables, right? All the partials of all of the output coordinates. Right? So I've got various output coordinates that I could take partials with respect to all the various input variables. I want all of them to equal. To be again, if we want to say that L mimics F, then I want it to mimic F in every possible first order sense. And so, so there's the requirements, and I claim this is the function that does it. Now, in order to write that down, I've got to define this thing, and this is it's kind of like the gradient that we wrote down. This is a thing that we're going to write down to keep our formula more sort of compact, and we don't want it gets out of hand, right? When you have an entire array of different terms. So very convenient notationally, but other than that, it's kind of playing the role of the gradient here. I claim that this is the function that does it. Again, this is something you can confirm for yourselves. You can just write this down. I don't suggest that you do this for general n and m. N and m being the number of input and output variables. Just pick like n equals 2 and m equals 3 or something. You pick some nice small numbers, and then you can just confirm directly. You can compute all 6 of the partial derivatives, and sure enough, this does what it's supposed to do. Okay, so again, healthy exercise. I hope you'll take a whack at that. Real quick, last thing I want to observe. Notice that in this first column, and again, this is the magic matrix that does it, this thing I'm calling df. In that first column, we're always taking the partial derivatives with respect to the first input variable. right? And then et cetera. So the way I like to say it is the columns correspond to input variables. Columns correspond to input variables. And then you'll also notice that the rows, take this first row, we're taking all of the various partials of F1. The rows correspond to output coordinates, or output variables, you might call them. So this is important. If you aren't careful with this rule, you can accidentally transpose your matrix, right? And that's really wrong. It gives you wildly wrong answers, and it's very, very important that we get this straight. So make sure to pay careful attention there. Columns correspond to input variables. Rows correspond to output variables. And make sure to, again, it's not an arbitrary choice. This is, since we are using linear algebra to make this work, subject to the standard conventions of linear algebra, it has to be this way. And if you transpose it, it doesn't work. Yes?
Is this like the Jacobian?
Yes, it is. That's right. We will eventually find many uses for this matrix. For the moment, I don't even want to use that term just yet. You're absolutely right. I'm not going to use that term just yet. I just, for the moment, want to think of this as, this is a notational shorthand for the thing that if I put in there makes this linear approximation actually work. Okay, all right. We'll call it a day right here. See y'all later. Have a good, we're doing okay. Have a good Wednesday. See you on Friday. Oh, and if you came in after I did attendance, as usual, make sure to come and make sure I mark you down. All right.